Good morning everyone, and this is the first video of the new series that will cover the basic concept and summary of the series on financial mathematics by MIT OpenCourseWare. So this series you can think like it is a prerequisite you need to cover this series and the basic sum up of the series that is taught by a PhD professor and experienced person. So it will be the sum up of the series and basic concept and key point you have to remember from the series. Let me show you the series that we will follow, and this is the series we will follow, and this is series by MIT on financial mathematics, and we will cover second chapter linear algebra. So let's start the series. So let me get back to our board and we will start there. There is okay. So we will start linear algebra. So most important topic in linear algebra is matrices. Everyone have learned about matrices in their school. So let me cover it fast. So matrices is uh, writing a data in a form of m by n. So here we will write row entry and here it will be the column entry. Okay, row like 2 3 4 5 6 7 8 9 10. This you can call a matrix, and in a more finance way you can form a matrix like this. Here you can write company name, Google, Tesla, Meta, and here you can write date 7 8 9 and stock price. So it will help you in your analysis and computing various tasks. So after we understand what is matrix, there is a very important topic called eigenvalue and eigenvector. So whenever we do any kind of transformation, so let's say it is matrix A and this is matrix B, and this is a transformation matrix. So let's say it is a rotation matrix. Okay, so let's say our A matrix is coordinate point this. After the rotation, this can be here, right? Okay, so all the data points you can see, any data point can change. So let's say there is so many data point in our Cartesian system. So if we transform it, everything can transform, right? But there are some kind of vector, or you can say data point, that that do not change its position, just it's scaled by any factor. It do not change any position, it just scaled by any factor, and that kind of vector, or this vector is called eigenvector. And the scale by which it scaled, the number is called eigenvalue. The eigenvalue is a scale number, that is a factor that scaled the eigenvector. So in more definite way, so you can let's say there is a matrix transformation matrix A, and after transformation we get eigenvector V, and its eigenvalue is eigenvalue, let's say lambda. So Eigen so equation of eigenvector and value is a upon vector is lambda v. So here a is our matrix and v is a eigenvector and lambda is eigenvalue. So this is the form we show our eigenvalue and eigenvector. And to find eigenvalue and how to, you can say how to find value, eigenvalue. So to find eigenvalue, there is a formula. Let me check the formula right. Okay. Determinant of a minus lambda I, right? Yeah. Here I is identity matrix. I upon yeah, product by eigenvector equal to 0. So this is the formula to find eigenvalue. So let's take an example and find the eigenvalue. Let's take a matrix A called 2 1 1 2, right? And okay. So for example, sorry. For example, let's say A is 1 2 and by this formula we can find there is a eigenvalue value of 1 and 3 and 1 and vector are 1 upon 1 and 1 upon minus 1. Okay. So you would say where we use eigenvalue or eigenvector. It is very important concept when you run PCA, principal component analysis, where it is used to reduce the dimension of data, or you can let's say your data in 5D space, you can convert it into 2D space and show the data in is eigen vector. So it is a called principal component analysis. It is very useful concept in ML and also in Quant finance, where you convert your data into simpler dimension. Okay. And for portfolio optimization, it is also very useful. Another concept they discussed is diagonalization. Diagonalization. Okay. So it is concept. Let me tell you what is diagonal vector. Diagonal matrix. So it is a matrix where all the data are in its diagonal. It is right, I guess. So all the data will be in the form of diagonal, right? See, 2 0 0. It is a diagonal matrix. So diagonalization is a process where you convert your matrices into a matrix where you show all the data in its diagonal. So diagonalization is that process. Okay. Sorry about that. Array. So you would say why we use diagonal matrix? Why, right? it is very easy to compute. You, if your data is very big, let's say you have 10,000 stock, to compute that it will take very much time. So for reducing, you will convert the matrix into diagonal matrix, and operation like dot product or finding exponent is very fast to compute. So you have to remember that the a matrix, let's say matrix A is diagonalizable if it can be written by in the form of A equal to B T P inverse, right, where D is diagonal matrix and P is a matrix of eigenvector. Okay, P is a value of eigenvector. So this process involved, we have to find the um, diagonal matrix and eigenvector matrix. So we have to find in order to compute that. Okay, uh, and then for example, let's say A is our matrix 4 2 1 3, right, and we have eigenvalue of 5 and 2, and eigenvector is 1 1 and -1 2, right. So by the formula this, you can find. So let me write the formula is 4 2 1 3. 4 1 2 3, like let me write the. So yeah, 4. Yeah, and our let me define you our P matrix. Okay, our P matrix is, I have computed that, so let me show it. Okay, wait a second. Our P matrix is 1 1 1 -2, right, and our P inverse matrix will be by the inverse formula, right. Let's say P inverse formula is 1 upon determinant of P upon D minus C minus B and A. Okay, and by this formula the answer is P inverse is our 2 pi 3 1 pi 3 1 pi 3 and minus 1 pi 3. So if we put this all value in the formula, we can find our diagonal matrix. Okay, and then yeah, so let's we move to next topic. It is very important topic, EVD, eigen value decomposition, and also SVD, single value decomposition. So what we mean by decomposition is, let's say uh, a, a point or a vector is, let's say there is a cube, and after some transformer, it has become tilted, let's say big and tilted cube. So we have to decompose this transformation into simpler transformation, like scaling plus rotation, and also many transformation. So this is called decomposition. We are dividing a space or a transformation into simpler space. Or here eigenvalue decomposition is for symmetric matrix. Symmetric matrices are the matrices who is similar, right? This and this value are similar, this and this, like this symmetric matrix. Okay, so let's get into a definition. EVD is method to break, let's say, a square matrix or a symmetric matrix. Square matrix, it means the dimension should be same, m to m or n to n. Square matrix into component for a matrix. Okay, into component that reveal intrinsic intrinsic properties, and its eigenvalue and vector are given by this formula. So let's say A is n by n matrix, n by n matrix, and its eigenvalue decomposition is A equal to QA. We have seen this. Okay, Q inverse. So here we have to remember Q is n by n matrix, and it is also n by n matrix, and uh, sorry, okay, it is not A, sorry, my mistake. It is lambda, I guess. Okay, where this is diagonal matrix. So let's see condition for EVD. So first condition, we have stated that matrix should be square, should be square matrix. Okay, and we have we should have a diagonalizable matrix. It means that a matrix that can be diagonalized, means its all value can be converted into its diagonal form, and it is not true in all case. Not all matrices can be diagonalizable. So that is a thing one should be remember. So diagonalizable. Okay. So let's see steps to compute that. To compute EVD. Okay. So first is we have to find lambda eigenvalue. So its formula we have seen that determinants, by this formula we can find lambda value, and after finding lambda value we have to find eigenvector. So by formula A minus lambda I, we can find that. and then we can then then we have to find q matrix and diagonal matrix. Let's say so it's and let's limitation discuss limitation of EVT. So we have we know that it's only work for square matrix, and sometime for non-symmetric, sometime eigenvalue eigenvalue can be complex. So it is, and not all matrices are diagonalizable. So to overcome this limitation, we have another method called SVD, single value decomposition. It is very powerful method, not as much powerful than eigenvector, but still. So it's do the same. It's decompose alter transformation into intrinsic transformation that we can understand. So to compute and plus point is that for any matrix, it uh, it have no condition that it should be square matrix. So we can have any matrix m into n, any matrix A with m into n dimension. So its formula is matrix A equal to u upon diagonal matrix on V transpose, मतलब eigen orthogonal matrix. Okay, so where u is m into m orthogonal matrix. Orthogonal matrix are matrix whose what we say, if we product it with its transpose, it identity matrix is the result. So that is the orthogonal matrix. Okay, matrix summation m into n. This diagonal matrix can be m into n, which is diagonal matrix with singular value like sigma. Okay, and uh, v v is like we say orthogonal matrix. So how to compute that? So for computing SVD, first step is to compute, to have a value of A transpose A and uh, A T. So so eigen value of this matrix will give you singular value that we call sigma square. Okay, and eigenvector of vector of A T matrix from U, and eigen vector of A from V. So we will get U and V matrices. So it is a eigenvector of a dot a transpose in U and eigenvector of a transpose dot a in V. So we get our U and A U and V matrices. So then we construct U sigma U and this matrices. Okay. So features of SVD is work for it first it work for all matrices M into N. Second, uh, singular value are always non-negative. Always non-negative. And it provide orthogonal base for row and column space of A. So our basis of right say normal origin base convert into orthogonal basis. Okay. So uh, let's compare important feature of EVD and SVD. Okay. So only square is there, any matrix. Here Q eigenvector from Q is orthogonal, and here U and V are orthogonal. Okay. And why SVD is feature? Because first it is universal, and SVD is robust for ill value, ill condition, sorry, or single value matrix, singular matrices. And SVD is more used in PCA and many tasks of image compression and anything. So that sum up whole first lecture of MIT Open Courseware course on financial mathematics. I hope you like my explanation, and I will try to improve every day by video. Thank you for listening. Bye.